Hi everyone, I wanted to go over today how to do lecture assignment number 6, at least a couple of the key exercises I noticed a lot of people had trouble with, and I guess I could have predicted people would have trouble with them. They're pretty hard. So I'm just gonna, I just want to show you how to do these because, after seeing so many people had trouble with this and a lot of people skipped over it, I'm gonna put this on the test. So, or something like this, to test to make sure you understand how to do this. So first one I want to talk about here is this exercise. I'm going to, by the way, to complete this, I'm going to be using the draw tool. And I really suggest you get the draw tool for Word. It's free. You can add it on easily. If you just Google, add draw tab in Word, you'll find it easily. So, you can see with this thing, you can draw and do whatever you like. You can erase it too. So it's very useful though. So I'm going to use that to do this here. So it says in the diagram to the right, use Steno's principles and put the following list of events in order. So we want to sort out what came first and what came last in this diagram right here that we're looking at. So a good place to start out is just from the top, okay? Because usually things at the top at the surface were deposited most recently. Okay, so I'm going to be going from most recent to oldest. Okay, so the most recent thing, you might think, well, what's exposed at the surface? We have the limestone and we have also this orange dike. So which one came most recent? And the answer to that is the dike. Why? Because of Steno's principle of cross-cutting. Okay, the dike cut through the limestone, so therefore the limestone must have been there before the dike. Okay, so I'm going to put the dike number 1. I'm going to put 1 because it's most recent. Second most recent, oh wait, look, I already made a mistake. Notice down here, this granite is cutting the dike, right? So again, if the dike cuts the limestone, it had to come after the limestone, and the granite cuts the dike, so the granite had to come after the dike. So this is actually, sorry, down here is number 1. My bad. Forgot how to do my own exercise. Okay, number 2 is the dike. Now, due to principle of superposition, probably the limestone here is number 3 because it's on top of the coquina, which we'll put as number 4. Now notice that between the coquina and the beds beneath it, there's an angular unconformity, right? These are at an angle. You can see the do you all see how the surface here is rugged and how there's cobbles? Do you all see that? There's like cobbles of the sandstone in the coquina. That's an erosional surface. Therefore, there must be an unconformity there. Okay, whereas this surface is perfectly flat, and that's probably a conformable surface. Okay, so probably now assuming that these were just tilted, there's an unconformity. So the fifth thing that happened is this unconformity in the tilting of the layers. Okay, so I'm going to put a 5 that kind of represents the layer here. All right, so that's number 5. Number 6 is probably going to be the sandstone. And beneath the sandstone, you can see is the breccia. And number 8 is the shale. Okay. So is it conceivable that these beds were actually in the opposite, and the shale is number 6, breccia is number 7, sandstone's 8? That's actually conceivable if the beds were tilted so much they were overturned. But assume that they were not overturned. Okay. So in that, you can see that the sandstone, the breccia is beneath the sandstone, and the shale is beneath the breccia. Okay, so that's how you do that. So, all I drew upon there were the laws of cross-cutting and the laws of superposition to get that answer. Okay, and the law of original horizontality as well, because remember, these beds are always laid down initially horizontally. All right, so let's move on. This is the big exercise that caused people a lot of consternation, and it's this one on correlating the what do you call them? The rock units. So I'm going to take this guy here just to kind of help myself. I'm just going to put it in front of the text like that for now, and I'm going to just move it wherever I want. And I'm going to kind of put him right here. So I'm kind of moving things around. That, by the way, I just want to give you guys a tip. This whole thing where you click layout option and put in front of text, It's a really good way of kind of moving stuff around freely and answering questions too if you choose to just edit these things electronically. So I'm just moving this right here so that I can see it more easily. Okay, so I'm going to put it right there. And let's take a look. So basically the way this works is we have to correlate these three sequences we see here, right? So we have three sequences of rocks, three, layers of strata, and we want to match them all up by the kind of match them up like by time. Okay, so which ones were deposited at the same time? A very important key point here is that just because you have the same kind of rock unit doesn't mean they were deposited at the same time. So a lot of people, for example, tried to do this. They tried to match this laminated sandstone to this laminated sandstone. Okay, those don't correlate just because it's a sandstone, a laminated sandstone. No, because why? The same kind of, the same, I can put it like this. Sometimes different at the same time in the same kind of general region, different rocks can be deposited at the same time. Okay, and that's not surprising, right? Like if you go, for example, go out to Indian Point and go out to Sunset Lake, and you'll see that on one side, of the lagoon, you're getting deposition of sand, and on one side of the lagoon, other side of the lagoon, you're getting deposition of mud. Okay, so they're going to make someday two different rocks that are of the same age. So beware that pitfall. All right, so there's a few things we can do to start here. So number one, we have volcanic ages here. So let's put those in and correlate them to the actual, the absolute ages to geologic age. So we see V is 163. Okay, so I'm going to write 163. W is also 163. Okay, so we know right away, here's a correlation. Okay, maybe I should use that red for the correlations. Okay, so there's a correlation right there because it's the same age. All right, now X is 247. So here's X, 247. Y is 64. Where's Y? It's up here. Okay. Z is 318. Okay. Okay, so now what you can do is correlate these ages that you get here to, oh, sorry, I wrote 247, sorry. There we go. Let me erase that. Somehow that got messed up. Okay, so let's correlate all these things, these numbers, absolute dates, to geologic time periods, okay? So 163, if you go to your geologic time scale and look up 163 million years ago, you'll realize that that was in the middle of the Jurassic, okay? So I'm going to put a J here for Jurassic. J for Jurassic, okay? Then 247, if you look that up, geologic time scale, you'll realize that that was during the Permian. Okay, so I'm going to put a P there for Permian. And then if you look up the 318 here, you'll see that that is right on the Pennsylvanian Mississippian boundary. Okay, it's literally the boundary. 318 is literally the boundary between Pennsylvania and Mississippian. Okay, so I'm going to put here kind of M going this way and we kind of do a fancy P with kind of a thick P like that for Pennsylvania to discriminate between Pennsylvania and Permian. Okay, so it's the boundary. Everything above that is Pennsylvania and everything below it is Mississippian. Okay, 64 is really close to the boundary of the Cretaceous, so we're going to put C here for Cretaceous. Okay, so those are all the boundaries we have. The absolute ages we have from volcanic layers. Now, let's try to correlate index fossils. So we have this diagram of index fossils if we look at this kind of weird shell-like thing, we notice that this correlates to this right here, which was laid down in the Cretaceous, right? You all see that? So this thing is this right here. So we see that this must correlate here, and we notice also they're both clay stones, so that makes it really easy. Okay, so now you might be tempted to go straight across and go to connect this to this limestone, but don't do that, because even though it's at the same height, see, different rock units are thicker in different places. And also, I want to point out something else. Not all rock units are going to be present everywhere, okay? Sometimes you have rock units that are missing. I tried to make a big deal out of that during the lecture. So you'll notice that this has the same fossils, so this all correlates, right? And you can see that this is all Cretaceous, which makes sense because this volcanic layer is in the Cretaceous too. So we're going to put a big C here for Cretaceous layer. Okay. Now we have this weird fossil right here. Let's see if we can correlate that. It looks like what? Maybe, does it look like this guy? Okay, kind of looks like that guy, right? But we also see here that this layer also has these things, these kind of curled up ammonite fossils, and those are definitely this one, which is during the Jurassic. Okay, so we know that this is Jurassic. This is also Cretaceous here. Okay, so I'm just, I'm going little by little and just kind of uncovering the puzzle pieces here. Okay, so we know that, and this is to kind of point out that you can have a rock unit that is both, part of it is in the Jurassic, part of it's in the Cretaceous, right? That's okay. So we know that there's a Cretaceous-Jurassic boundary somewhere in here, right? There's the boundary between the Jurassic and the Cretaceous. So let's look at this guy. What kind of fossil is this? It belongs to, looks like this one right here, right? So that's Triassic. Okay, I don't know if you can hear my kids crying in the background, but there are some disasters taking place. So I'm a little distracted. Okay, so this is Triassic. Okay, right? I'm right about that, right? This one is this, right? Okay, I think that's correct. Okay, so that's Triassic. So that makes sense. Triassic here, Jurassic on top, Cretaceous on top. Seems like all these beds are very conformable. Okay, let's take a look here. We have, what are these little things? They're actually a type of rugose coral. We'll learn about that later. Seems to conform to this. So that's Pennsylvanian. Right, that's the Pennsylvanian period. So I'm going to put a thick P here for Pennsylvanian. And notice that the Permian is right above it, so that makes sense. Okay, so again, this claystone layer was deposited both in this claystone right here was deposited both in the Permian and in the Pennsylvanian as well. Okay, now these fossils right here are also, I see, Pennsylvanian as well. Okay, so this correlates to this, and I'm going to make a guess that probably this claystone. Let's see, what is this fossil right here? What is this right here, do you think? It's probably, looks like it's probably this one. Okay, so that is Triassic. So, hey, look, this is Triassic. This is Triassic. So probably this limestone here is Triassic, and this all correlates like that. And that makes sense because this volcanic layer is at the bottom of the Permian. Okay. So this is Permian, Pennsylvanian. This is Pennsylvanian. I'm guessing that this is probably Pennsylvanian right here. So I'm going to guess that this is Pennsylvanian as well. Okay. Now, let's see, what do we have? We have this fossil, and how does this one correlate? That's probably, looks like this guy, right? So that's Mississippian. Okay. So I'm going to put an M for Mississippian. And you can see that I can't really, like, what is this laminated sandstone here? I don't know. It doesn't matter. You don't have to match everything up. But you can see that this sandstone here is Mississippian. How do we know? Because it's being cut by a Mississippi, Mississippian age. Everything below this volcanic ash layer, remember we said this in the beginning, is Mississippian, right? So we know that this sandstone here is Mississippian, so we can correlate that to that. You know, does this laminated sandstone possibly correlate? You know, maybe. I don't know. We don't have any evidence to say yes or no. Okay. You'll notice that I like this exercise because, you know, it's messy and it's this is just reality. You know, you can't always correlate everything. It doesn't work out perfectly all the time when you're trying to correlate strata in geology, okay? Oh, I missed this guy. So this guy looks like this fossil is this one here, which is tertiary. Okay, so this is tertiary. I'm going to put kind of fancy double T here, thick T for tertiary. Now is, you know, again, we don't, like I said, we don't really know what, there's nothing above Cretaceous here in this unit. And is this coarse sandstone possibly correlated to that one? It's possible, but you know, we can maybe just put a question mark there. We just don't really know. Okay, but we definitely know that this coarse sandstone came sometime after the tertiary, because we see that it's law of superposition, right? It's all possible, but there could be an unconformity here. Now I'm going to get my other pen out, and I'm gonna maybe this yellow highlighter. Let's see. Yeah, that shows up. So let me highlight some unconformities. So let's take a look at these beds. Okay, we go pencil. Well, let's do it like this. We got Pennsylvanian, or now this is Pennsylvanian for sure in terms of the fossils, but there could be an unconformity here because we go, oh, I don't like this pen after all. Maybe I'll use this one. There could be a unconformity here, which would be a disconformity because it appears conformable. Maybe. We don't know. But we do know that this bed is for sure Pennsylvanian here, and this is for sure Triassic. So where's the Permian, right? There could be missing time right there. All right. Here we have, in this strata, we have Mississippian, Pennsylvanian, Permian, and we have Triassic, we have Jurassic, and we have Cretaceous. So this seems to be totally conformable. Okay, it seems like everything makes sense here. Here we have, right, Mississippian, Permian, Pennsylvanian. You know, is there a Permian bed? It seems possible. Maybe there is. Maybe there isn't. So we don't know if there's the conformity there or not. But take a look at this. This is a tilted layer. This is an angular unconformity. So we know that there is an unconformity right here. So it's quite possible, therefore, that this is also possibly an unconformity. Because see how there's a Permian unconformity here between the Pennsylvanian and the Triassic, or Permian and Triassic. So it's quite possible there's also an unconformity in those two spots. Okay. Then we go Triassic. We don't see a Jurassic here, but you know that we don't have any other evidence that there is a unconformity. You know, if somebody put an unconformity somewhere around here, I wouldn't, you know, disconformity, I wouldn't necessarily take off points. Okay. So anyway, and then it goes Cretaceous and then Tertiary. Okay, so I can see that this seems to be, or yeah, this seems to be all conformable above that. So those are the unconformities. I would say at the very least, I would have wanted students to get that unconformity. That one's obvious. You know, that's a angular unconformity. You should have been able to find that. Okay, last thing I wanted to mention is this one. Some people had some trouble with this one as well. These are different kinds of unconformities. Okay, so remember there's three types of unconformities. There's a disconformity, there's a nonconformity, there's an angular unconformity, okay? And there's one that's a conformable bed. All right, now this one down here is probably the conformable bed, okay? So I'm gonna put A for that. Where's the disconformity? Remember in disconformities, you have layers of sedimentary rock that are deposited on other sedimentary rocks, but there's an erosional surface between the two. So right here, there's eroded sedimentary rocks. That makes it easy for you. That one's B. Next is a nonconformity. Remember, in a nonconformity, you have sedimentary rocks deposited either upon a plutonic rock or a metamorphic rock. That's granite right here. Sandstone, shale, limestone on top of a granite. That's definitely going to be your C, your nonconformity. And angular unconformity, you can obviously see there's these tilted layers here. Deposited on top are sedimentary horizontal layers. So that's going to be your D. All right, so that's all I really wanted to do, and show you guys how to do those exercises. Like I said, there's going to be exercises like this on the midterm. Too many students just skipped over this stuff, and it's very, very, very important. These were the very important exercises. A lot of them got skipped over because they're difficult, and I admit they're difficult. But please don't, if you're having trouble with an assignment, let me know, because I can make videos like this walking you through it. All right, so, and I'm very willing to do that. So please don't be shy to ask for help if you're struggling. Anyway, that's all for right now, and I hope that in the future you're going to have be a little bit more willing to contact me if you need any help. So I'm signing out here now.